We did the first lesson. Na? Again, there were some of the terms like scientific notation, rounding off, uh, etc. Those things. Again, if you want me to do at the later stage, you please let me know. I will do it. Okay, children? Both of you? Vishak, is it fine? Anything related to chemistry part is done there. Okay. Okay. Now coming to second lesson. We are taking up the second lesson. Okay. And what is basically the flow of the second lesson? See here. The second lesson, the name of the lesson is Structure of Atom. Okay. It's the name of the lesson is Structure of Atom. Do you remember a similar lesson in class 9? Uh, there, basically, we were understanding the details about atoms. Okay. First, we understood the structure of atom, and there were a number of theories proposed, like the Thomson's theory, the watermelon model, or you call it as plum pudding model of atom. Okay. So basically, the lesson runs like this. Okay. To know the discovery of the electron, proton, and neutron, since it is about the structure of atom. So the first part of the lesson will be dealing with the way the electrons, protons, and neutrons were discovered. Okay. Then the Thomson's model, which describes the structure of atom, right? Same as what we learned in class 9, saying that it is the plum pudding model. The positively charged, the entire atom is spherical. Positive charge is spread all around, and negatively charged electrons are embedded here and there. So I'm not saying anything new. Same way, Rutherford's model, the gold foil experiment. So same concept. Okay, and if you remember the failure of the Rutherford's model, we were told at that time that an electron being charged particle in nature, when it is following a circular path, it is going to get accelerated towards the nucleus, and at one point of time, it should hit the nucleus, and the atom should be unstable in nature. But contrary to this expectation, the atom continues to remain stable. So there was something really wrong with the Rutherford's model, right? Do you remember all this? Hmm. Anyway, we are going to do it once again because this lesson may start from the beginning. So we'll do it once again. Okay. Then we will, the main focus of it is to understand the Bohr's atomic model. Okay. The Bohr's model. Right. So because for a very long time, Bohr's model dominated, and Bohr's model was much elaborate compared to the Rutherford's model. It gave a number of details about the atoms. Even today, we feel rather than using the quantum mechanical model, the Bohr's model works in a lot of places to study the chemical reactions. Okay, so we will understand in detail. So how the lesson progresses, I'm going to tell you. Okay, and finally, I'll tell you what we will do. So we will actually learn about how the electron, proton, neutrons were discovered, what experiments led to the discovery of electron, proton, neutron. Then we will talk about, based on the information about the electron, proton, and the neutrons, the Thomson's model came into picture. And the Thomson's model proposed the possible ways of arranging the protons and the electrons. When Thomson was discussing his model, the neutrons were not known. But later on, they were discovered, we can say. They were already there, but they were discovered. Then came Rutherford's model, which was based on an experiment called gold foil experiment. And he proposed, based on the observations he made in the gold foil experiment, he made certain observations and concluded that based on the observations, the structure of atom should be so and so. If you remember then the most of the positive charge is located inside the center of the atom called as nucleus. Electrons are present all around. Most of the space around the atom is empty, and the electrons are occupying them. And then you talked about the alpha particles. If alpha particle is going straight onto the nucleus, it will be returned back. Okay, if it is passing very close to the nucleus, it will get deflected. And if it is passing away from the nucleus, it will pass straight. So all these things we will. So after Rutherford's model, we will actually learn about the Bohr's model. But in order to understand the Bohr's model, in order to understand, in class 9, you were told that Bohr proposed that there are certain stationary energy states possible in atom. Okay. Only certain allowed stationary states are possible. And as long as electron revolves in those orbits, the electron's energy doesn't change. Okay. So, but we will take a long gap between this and that. Okay. That means after Rutherford's model, we are going to talk about what is required to understand the Bohr's model. Okay. We are going to talk about what is required to understand the Bohr's model. So this was the Rutherford's model. We will again, as I said, we will come back once again briefly, not in detail. So Thomson's model, Rutherford's model. After Rutherford's model, we will try to understand the atomic number, mass number, isobars, isotopes, and all that. Then the drawbacks of Rutherford's model. And if you see, the proper learning starts from here because all the other things were previously done in 9th standard. So what led to the development of the Bohr's model of atom? So we will try to understand the development leading to Bohr's model. It's not the Bohr's model right now. The development leading to Bohr's model. So we are going to analyze the light and we will talk about the dual nature of light. One is the wave nature of light. The other one is the particle nature of light. Okay. So in between Rutherford's and Bohr's model, we will explore light and connected experiments. So basically, we are going to explore the photoelectric effect and the black body radiation. Okay. Black body radiation as an introduction, and other than that, nothing. So we will not summarize its results and tally it, but we will understand what it is. Okay. After all of this, I told you, in between Rutherford's and Bohr's model, we will try to understand light, and using light, we will analyze the Bohr's model. Using light, the Bohr's model is going to be understood. Is the flow clear? Electron, proton, neutron, Thomson's model, Rutherford's model. After that, we need to learn the Bohr's model. But for understanding Bohr's model, we have to understand the light in a better way. So, connected topics with the light. Light has got wave nature, which has light has also got particle nature. So we will talk about particle nature being described or being the evidence of light having particle nature comes from the photoelectron effect and the black body radiation. So we will do it in detail and then only we will come to the Bohr's model. So far the flow is clear, children? Okay. Okay. After this, so though they have given you in the third line itself, but there is a considerable amount of work between Rutherford's model and Bohr's model. So we'll try to understand the Bohr's model after understanding the light. Okay. So after Rutherford's model, the dual behavior of light, then we will come to Bohr's model. Okay. After Bohr's model, we will understand that Bohr's model is also not very perfect. It's not correct. Okay. So we will try to go towards development leading to quantum mechanical model. Earlier we said development leading to Bohr's model. Now we are going to understand the developments leading to Bohr's model. So under that, we are going to talk about the de Broglie wavelength and Heisenberg uncertainty principle. Okay. So after understanding that, we will go into the quantum mechanical model. We call it as quantum mechanical model of atom. Under quantum mechanical model of atom, we will understand the latest ideas about the structure of atom. Okay. Latest idea about the structure of atom. And finally, with the structure of atom in hand, we are going to write the electronic configuration of the atoms. Is the flow of the lesson clear? Okay. Vishak, clear? Okay. Now, what I am going to do is, let us first know the electronic configuration. Okay. Then we will do the top down. So we are going to first learn the electronic configuration and related topics. Let us know the current structure of atom, how the electrons are distributed, where are they located, and then we will go and make again an attempt to understand the picture. So we are going to start with the electronic configuration. That is the last topic of the lesson. Clear? Once we know the atom in and out, then it will become more easier for us to understand the entire procedure. Okay? Are we clear what we are going to do? Okay. So we will understand the electronic configuration today. Okay. Right. So to understand the electronic configuration, okay, we will look at, I told you the quantum mechanical model is going to help. Okay. So the what is quantum mechanical model, and what is the treatment of an atom under the quantum mechanical model? All those things I am not going to talk more. Okay. We are going to directly talk about the electronic configuration. Okay. So let me start with it. Okay. I'll tell you, if you have to follow the textbook, from where you will learn is what I'm trying to look to. Basically, you can start with this. What I'm teaching you today, you can start with 2.6.1. Okay. But listening is more important today. Not, you may not understand everything from that section also when you read, but try to understand what I'm discussing. Okay. Say I have an equation. Okay. Say 2x plus 3y is equal to 5. Tell me how many solutions will be possible with this equation. How many solutions are possible? If x is equal to 1 and 1 only. If x is 2, what will be the value of y? Okay. If x is equal to 1, what will be the value of y? Okay. If x is equal to 0, what will be the value? So how many possible values are there? Is only 0, 1 and 2 possible for x? Infinite. So this equation is the equation for a line and or a linear equation in two variables, and you can have infinite solutions. Infinite solutions, correct? Like that, an electron in the quantum mechanical model is proposed to have a mathematical expression called as Schrodinger wave equation. We will come back to all these terms once again. Under quantum mechanical model, an electron is treated as a wave, which is represented by an equation called as Schrodinger wave equation. Okay. Like this equation have got infinite solutions. This equation also has got some solutions. Okay. An electron in quantum mechanical model is treated as a wave. Not only as a wave, it is also as a particle it is being treated, but basically we call it as a wave function. So an electron is, the duality of electron is taken. Okay. So don't understand the duality, no problem. So an electron in quantum mechanical model is described with the help of an equation called as Schrodinger wave equation. Like how this equation has got some solutions. Likewise, the Schrodinger wave equation also describes the solutions in terms of k. Supposing I want to describe one of the possible solutions, how will I describe? I'll say if x is equal to 0, y is equal to 5 by 3. Correct, children? So I will define the solutions in terms of x and y. I'll state the solutions of this equation in terms of x and y. If x is equal to 1, then y is equal to 1. Na? So I am stating the solution by quoting what is x and what is y, correct? The infinite solutions are going to be quoted in terms of x and y. Likewise, the solutions of Schrodinger wave equations are described with the help of 3 quantum numbers. Okay. namely the principal quantum number, okay, like X and Y. How do you describe? There are infinite solutions. You told me, right? There are infinite. But how do you define even the first set of the solution? You will say X is equal to so much, so Y is equal to so much. So this is one solution. So you describe the infinite solutions in terms of X and Y. Similarly, the solutions of Schrodinger wave equation can be described by using three quantum numbers. Any problem with this? Okay. Now the quantum numbers like X, Y here, the quantum numbers which are used here are namely principal quantum number. Number two, the azimuthal quantum number. The third one is magnetic quantum number. And we introduce the fourth quantum number from our side, which is called as spin quantum number, because we still wanted some more clarity regarding electrons. Is it okay? We needed some more clarity. So we will add another quantum number called as spin quantum number. The Schrodinger wave equation solutions are described in terms of three quantum numbers, namely principal, azimuthal, and magnetic quantum number. And the fourth quantum number is introduced from our side to add some more details to the electronic configuration. Are we clear? Up to this, any problem? Okay. Now, what can be the value of X? What can be the value of X? It can be a negative number. It can be a positive number. It can be zero. Correct? Isn't it? Okay. So there can be, X can have any values, na? Can be negative, positive, or zero, right? Fractional values, anything. Okay. Like that. Okay. Like that. You will, like that. The principal quantum numbers can't have any value. There are certain allowed values. Okay. There is a restriction. See, what is the range? What can be the values of X? The range is it can have a positive number, zero, negative number. So this is the range. Na? The values will lie within this, correct? Which incidentally includes every possible value, right? Likewise, the principal quantum number values also has got a range. What is that? It can be 1, 2, 3, and so on. Any natural number. The principal quantum number values will be any natural numbers. It is usually represented with the symbol N. Okay. And basically, it signifies the number of the shell number. We can put it not number of shells. Instead, we will put it as shell number. So this tells me the shell detail. Is it okay? I'm just introducing the electronic configuration. So some of the information I may not disclose it. So principal quantum number is represented with the symbol N. N in mathematics, like no, let the father's age be X. And the madri. N is a something which people in chemistry like. So N, principal quantum number. Whereas in first lesson, we used N for number of moles. Okay. So it can be used in many aspects. Okay. Many ways. So principal quantum number is represented with N and marks what it tells you about the shell detail. Where is the electron located? Is the electron located in the first shell, second shell, third shell? Again, I will remind you that we are learning the electronic configuration. All the discussion that I have made so far is electronic configuration related only. Clear, children? Okay. Now, coming to the principal quantum number. The principal quantum number values can range from n to infinity. N is equal to 1 to infinity. It cannot have zero value. It cannot have a fractional value. It cannot have a negative value. The allowed value ranges from 1 to infinity. What do they indicate? They indicate the shell number. So it was actually K shell, which was recognized by the Bohr's model. The K shell's principal quantum number value is 1. The L shell, the second shell's principal quantum number value is 2. the third shell is called as M shell. That means during Bohr theory itself, these quantum number values came into light. The principal quantum numbers or the shell numbers are the information provided by for the electron. Where is it located? Is it located in the first shell, second shell, third shell, 10th shell, 15th shell, or infinite shell? So principal quantum number tells about the location of the electron. Clear? The rough location of the electron. Clear, children? What are the possible values? It can be starting from 1, any higher value. Is it okay? Okay. Now, so what does it mean? Supposing the principal quantum number is 3, that means for an electron, the principal quantum number is 3. That means electron is located in the third shell. Okay. If the principal quantum number of an electron is 6, then the electron is located in the sixth shell. I hope that is clear. Okay. The azimuthal quantum number, okay, or the angular quantum number, you also call it as angular quantum number or angular momentum quantum number. It is indicated by the symbol L, small l. And what does it indicate? It indicates the subshell. It indicates the subshell. Where are the subshells located? They are the specific regions inside the shell. They are the specific regions inside the shell with no hard and fast boundary. Can there be a boundary, children? We are talking about an atom. This is the nucleus. Is there, see, is there a boundary segregating the protons and the neutrons from the electrons? Is there a boundary, children? Is there a wall standing between the protons, neutrons, and the electrons outside? No, because what we are learning is atom. An atom is the smallest entity. And in the smallest entity, don't expect somebody to come and build a wall made up of some matter, correct? So what is nucleus basically? It's the region where the protons and neutrons are packed up tightly in a small region. We'll draw a line to demarcate the region where it is present. Similarly, is there any line present here, children? Saying that electrons are present within this region. Is there any boundary here? No. What we do, where are the electrons found? The electrons are found anywhere around this nucleus. So our line that we are drawing is trying to enclose the possible positions of the electron. Clear? Okay. Now, so within a shell, there are some subshells, okay, which have specific shapes. Which have specific shapes. Okay. Now, the L value will in turn depend upon the previous quantum number value, right? The L value will depend upon the like the value of X is defined. X is defined as 0. So Y is automatically defined based on the value of X, isn't it, children? If you say X is equal to 0, declaration is X is 0. So Y will automatically depend upon the X value. Same way, the principal quantum number is declared as, let us say, 1. Then the connected subshell will depend only on the principal quantum number. So it is governed by the principal quantum number, right? So the value that is allowed for L will be anything ranging from 0 to n minus 0 to n minus 1. Is that clear? Both of you? And it depends upon, see, the formula to calculate the L values is having n in it. That means, is it not dependent on n value? Okay. Vishak, is it fine? Okay. The magnetic quantum number values, what do they represent? I told you within the shell, there are some subshells. Okay. Within the shell, there are some subshells. Now, these subshells can be 1 in number or can be many in number, right? It can be 1 or it can be 3, it can be 5, or it can be 7, it can be 9. I'm giving you some numbers. Either it can be 1, the subshells can have 1 orientation, or 3 orientations, or 7 orientations, or 9 orientations, and so on. Okay. What are these actually? I told you within the shell lies the subshell. These subshells are going to have some orientation. These orientations which the subshell can show is indicated by the magnetic quantum number, indicated by the term M, or M subscript L, because M value will in turn depend upon the previous quantum number value. The L value depended on the N value. The magnetic quantum number value will depend in turn upon the L value. So what is the range for it? The range is from plus L to minus L. Okay. What do we call them? We will call them as orientation. Okay. Or we call them as orbitals. Orbitals. And if you want a very sensible word, I'll put it as regions or space. Is it okay? So within the shell lies the subshell. These subshells may be oriented in different directions. Those orientations are indicated by ML values. Is it okay? Now I told you a magnetic quantum number defines the orbital or space. Now these orbitals or the spaces, one such space or one such orbital can hold a maximum of 2 electrons in it. An orbital can hold a maximum of 2 electrons. And those 2 electrons are given or assigned the spin assigned. You remember I told you that the quantum mechanical model allows us to describe the solution in terms of only 3 quantum number values. The fourth one is introduced by us. So each orbital can have 2 electrons, and the 2 electrons are assigned plus half and minus half spin, indicating if the electron is spinning on its axis in clockwise direction, we will say plus half. If an electron is on its axis spinning on the anti-clockwise direction, we will say it is minus half. This was introduced by us to satisfy our needs. Fine, children? Any doubt in this? You may not make meaning if you have not learnt this, but with this we will progress and do the electronic confirmation. Okay, up to this something is clear at least? The last part is, see, in a shell, there are regions, specific shapes. Okay. In a particular shell, the electrons are present in certain subshells. These subshells have got peculiar shapes. Okay. These subshells, these shapes have different orientations. The number of orientations is indicated by the magnetic quantum number. These orientations are also called as orbitals. What is an orbital? In a crude way, it is a space, a region, an enclosure. Okay, a space. That space or that orbital can have a maximum of only 2 electrons. Now, to distinguish one electron from the other, we are assigning the spin to it. We are assigning. Assigning means we are giving it. It's not result of the quantum mechanical model. So, the 2 electrons present in a single orbital must be distinguished. Na? They should be distinguished. I should be able to identify which electron is that. And the electron, update. So to identify the electron, present 2 electrons in an orbital, I assign one electron plus half spin and another electron minus half spin. Why? Because an electron is not simply a dot. It's spinning. It's charged particle and it keeps spinning and revolving around the nucleus. So in an atom, it's going to have a spin, plus it's also going to have a revolution. Around the nucleus, it keeps revolving. As like our planets. Remember, our planets around the sun will have the rotation on its axis. Also, it keeps revolving around the sun. Like that, the electrons also are revolving around the nucleus. But when they revolve, they keep spinning also. If the spin is clockwise spin, then we say it is plus half. If the spin is anti-clockwise spin, then we say it is minus half. Clear? It could be spinning in anti-clockwise and progressing, or it could be spinning in clockwise and progressing. Is it okay? Uh, They are all synonymous to one another. Orbital and orientation is synonymous to one another. We will start using orbitals later on. Okay, right now you need to understand the orientation. Okay, so can we progress now? I'm going to now what I'm going to do is I'm going to take up the first issue and break down the information. So you please note down. Have you noted down these informations? Vishak? Hmm. Basically, I want you to note down what are the ranges, what is the possible values. Okay, now coming to we'll try to understand the first shell now. Okay, so remember the principal quantum number speaks about the shell. The azimuthal quantum number speaks about the subshell. The magnetic quantum number speaks about the various orientations of these subshell called orbitals. And the spin quantum number finally talks about how to distinguish one electron from the other. And the possible values. Remember, it's not 1, 0, 1, 2, 3, and so on. This is 0 to n minus 1. I'm just writing it for you to have a look easily. Okay, plus L to minus L. And this is plus half and minus. Okay, now, so I'm going to take the first shell, the K shell. Remember, okay, tell me before that, how many electrons are possible in the K shell? Was there any formula to identify the number of electrons in each shell? What, remember? 2, 8. Was there any formula for it? Was it not 2n square? The number of electrons in a given shell used to be 2n square, remember? Substitute the value of n. See whether you are getting these values. 2n square. Isn't it 2 times 1 square? K value, K is the first shell, L is the second shell, M is the third, N is the fourth. So can we say 2 times 1 square is 2? 2 times 2 square is 8. How many electrons in the third shell? 2 times 18. Yes, Vishak, how many in the last? So now last one will be 2 times 16, so 32. Then next shell, fifth shell, though we don't have the name to it. Okay, we don't have a name, but what will be the number of electrons in it? 2 times 5 square, 50. Was it okay? And I'll tell you why we don't have a name for all this, okay? Which is not commonly used. I'm not saying there is no name. There's no commonly used. Because the fifth shell never gets fully filled. That's why. Okay, so we'll try to talk about this now. So I am analyzing the first shell. So how many electrons are possible in the first shell? Only 2. Okay, so come back. Now, the K shell. What's the principal quantum number? 1. Did I not say principal quantum number tells you the shell number? Okay, so n is equal to 1. So what will be the azimuthal quantum number value for it? What is the range? It will be 0, 0 to 1 minus 1, which will be 0 only, right? Okay, now what is the 0 here? Now I'm going to give you a gift. Okay, I'm going to give you a gift. And on top of it is written as 0. right? I have given you gift, na? So there is a gift which is titled as 0. The 0 does not indicate that no gift was given to you. I gave you a gift titled 0. Got it? Something like in your TV, you may have, earlier we used to have channels. The channel number 0. There will be a channel numbered 0. Here also there is a subshell numbered 0. The 0 here does not represent the quantity. Got it? Got it? Okay. So the first shell, we'll call it as first shell, has, can we say only one subshell? Namely, L is equal to 0. Understood? Okay. Now these subshells also have names. These subshells also have names. If L is equal to 0, then you call it as S subshell. If L is 1, we call it P subshell. L is 2, we call it D subshell. L is 3, we call it F. L is 4, we call it S, P, D, F, G, 5, H, and so on. When you again come to the chance of using S, you miss it. And give the next alphabet. So if L is 0, what would you otherwise call it, children? You would call it as S. So you will call it as S subshell. Got it? Okay. So in the first shell, there is only one subshell, namely S subshell, whose L value is 0. Got it? Okay. What is subshell? Within a shell, a smaller region is said to be subshell. Okay. Now coming to this S subshell. What will ML value indicate? Remember, what does the ML value indicate? The magnetic quantum number indicates the orientation. Or you call it as orbital later on. What are the values? What is the range for it? Plus L2 minus L. That means it depends upon the L value. Plus L2 minus L. So what is the L value that we are talking about? L is equal to 0. So shouldn't it be plus 0, 2 minus 0? In other words, it is simply 0, right? Again, 0 does not indicate that there is nothing existing there. There is something whose label is 0. There is some object, some gift, which is having a label called 0. Got it? So this is the orientation. What is the orientation? When I get only one M value, see, for the L is equal to 0 or S subshell, I'm getting only one orientation. Okay. Now, which object in the world will have one orientation? What am I talking about? Supposing I have a pen with me. This is my pen. Fine. In how many directions can I point my nib, children? In how many orientations are possible for this pen? In other words, I'm asking, in how many directions can I point this pen? Infinite. Is it okay? Infinite. But which object will have no change in the orientation? If I take a sphere, is it pointed towards north, south, northeast, southwest, etc., etc.? No. So the only one orientation, remember I told you, first shell has only one subshell, namely S subshell, whose L value is 0, has only one orientation. So which can have only one orientation? Only a sphere can have one orientation. Is it clear? Okay. Now, what is this again? Come again. Now, what is this? Did I not call it as orientation? Or I called it as orbital? Or later I called it crudely as space. It's the space or a region in which how many electrons can be present? An orbital 2. One electron having clockwise spin, the other electron having anti-clockwise spin. So we have completed the breakdown of the first shell. How many electrons do you see in this? The first shell has only one subshell, which can have only one orientation or one orbital. That one orbital has got how many electrons? 2. So that is what we said here, no? That the K shell, the first shell will have only 2 electrons. Hmm? Now coming to second shell. So we must tally how many electrons in the second shell. Our results should be in the second. When I break down the second shell, how many electrons should I get? 8. So let us see. Vishak, is it okay so far? Okay. So break down the information about n is equal to 2. What will be the possible L values? Look at the range for L values. What is the range? 0 to n minus 1. So apply it 0 to 2 minus 1. Or in other words, it is 0 and 1. Correct? Correct? Okay. So what are the L values possible? L values can be 0 or can be 1. Okay. Now, the ML values will depend upon the L values, right? So L is equal to 0 represents S subshell, remember? Here we wrote here. What is L is equal to 1 going to represent? What is L is equal to 0 subshell called? P subshell. L is equal to 1 subshell will be called as P subshell. So can we say that the second shell has an S subshell and a P subshell? Okay. Now this again breakdown. This S subshell can have how many orientations? The orientations will depend upon the L value. So this S subshell, what will be L is equal to 0? What will be corresponding ML values? 0 again. So again one orientation. That means it is spherical. Clear? So the S is always spherical. Whether it belongs to first shell, second shell or 10th shell, it will be always spherical. Only one orientation. Clear? Okay. Now coming to P. P subshell. For L is equal to 1, what are the possible ML values? What is the range? Plus L, 0 and minus L, correct? So how many orientations are possible for the P subshell? 3. Can the P also be spherical? A spherically symmetrical orbital will have infinite orientations or no orientation, we can say, or one orientation, correct? Whichever side it turns, you can't identify. So we say it is one single orientation. So can the P also be having a spherical shape? Can a sphere have 3 different orientations? No. So what should be its shape? The shape for P is identified as a dumbbell. Okay. If it is a dumbbell, the dumbbell can be on the x-axis or can be on the y-axis or can be on the z-axis. Is it fine? The shape is dumbbell. In how many possible directions? In how many? What are the orientations of this dumbbell? It can be oriented on X. No, actually, it can be anywhere, infinite. But again, the solutions allow only certain possible values, Vishak. Is it okay? Every time, see, what is it actually? Say, for example, mm, I we have there is one zoo in Chennai. Where is it located? Vandalur Zoo. Hmm. Can I have my house inside Vandalur Zoo? Not allowed, na? Like that, not allowed. Like that, the quantum mechanical model allows certain orientations. It defines those orientations. That's all. We are sitting and studying them. Correct? We are sitting and studying them. The quantum mechanical model allows some orientations. Though for this dumbbell looking orbital, dumbbell looking subshell, infinite orientations are possible. But the quantum mechanical model puts a restriction where it can be. Either it can be on the x axis or exactly on y or exactly on the z axis. It is a result of the quantum mechanical model that we are studying. Are we clear? What did I call this magnetic quantum number? Did I not call it as orientation? Also orbital and also space. So these are the dumbbell looking spaces around the nucleus. So far what has happened? I'll tell you. The nucleus. Around the nucleus, the first shell. Within the first shell, which subshell is present? Within the first shell, which subshell is present? Which subshell or which subshells are present? Which subshell is present? S only. And what is the shape of this S? Spherical. So I'm going to draw. See, look at this now. So this is my nucleus. So this is the center. Around the nucleus, this is my S subshell of the first shell. This is the second shell. N is equal to 1 has only S subshell. N is equal to 2. Which subshells are present? Just now we worked on. N is equal to 2. Which subshells are present? S and P. So what are they looking like? If I use the red to indicate the second shell, this is the 2S. This is the S of the second shell. And this is the P of the second shell. Are you able to understand? Let us break this information again. Around the nucleus, the first shell electrons are present in a spherically looking electron pattern or spherically looking electron region. The first shell, this is the nucleus, the first shell has only a subshell. The electrons are scattered and they appear to be forming a spherical region. When we go to the second shell, there is a spherically looking electron cloud. Okay, the electrons form such a region. Or the electrons are found in this region also. This, the dumbbell looking region, the regions which look like dumbbell. So they are all interwoven. What we are doing is we are splitting them and studying them individually. So this is a space. This is a space. This is the region where the electron is found. How many electron is possible in this region? This is an orbital. If this is an orbital, how many electrons are possible in that region? An orbital can have a maximum of an orbital. What happened? An orbital can have a maximum of how many electrons? 2. So in this region, which I've shaded, 2 electrons. In this region, another 2, right? In this region, 2 more. I have talked only about the P. I have not talked about the 1s and 2s. I mean, the S in the first shell and S in the second shell. I have talked about P in the second shell. Clear? They will all be around the nucleus. Don't think that they are all, it is not going to be like this. Nucleus, first shell, second shell. Don't think there will be a dumbbell here, dumbbell here, dumbbell here. Understood? They are all electrons, are like all planets are pointed towards the solar, towards the sun. Likewise, all electrons, whether they are P or F, they will all be pointed towards the nucleus. So the P looks like this. This is Py. This is Px. This is Pz. This one is the first S of the first shell. This is the S of the second shell. All will be towards only the nucleus. நம்மளுக்கு இது பார்த்தா காம்ப்ளிகேட்டடா தெரியும். So we are splitting them. So how we break down nucleus? This is the S of the first shell. This is the S of the second shell. This is the Px of the second shell. This is the Py of the second shell. This is the Pz of the second shell. We are splitting them and seeing. Okay. Okay. So can we say this is a region? This one is a region. And how many electrons can be there in that space or that region or that orbital or that orientation? 2. So 2 in this. This is also the same, an orbital. How many in this? Here also 2. And also here also 2, na? Which makes a total of how many? Why is there a 2 there? Because the second shell has got 2 subshells, namely S and P. The S has got only one orbital or one orientation, which will also have 2 electrons, na? So 2 from the S, 2 from the second shell S subshell, and 6 more from the second shell P subshell. Totally makes how many? 8. And we are checking that only, no? Yes, Vishak, fine, ma? Okay. Can we break down the third one? N is equal to 3. L is equal to 0, 1, and 2, right? What will you call them? You will call them S, P, and D. What does S look like? Sphere. What does P look like? Dumbbell. Okay. ML. What is the possible orientation or orbital or space? Plus L2 minus L. So if L is equal to 0, what is the possible orientation? Can we say ML is equal to 0? Only one possible orientation. And one shape which has got only one possible orientation is sphere. So that concludes. So in the third shell, there is an S subshell, there is a P subshell, and there is a D subshell. Progressively, it is increasing. Na? In the first shell, only S was there. In the second shell, S and P. In the third shell, SPD. Clear? Okay. Now coming to P. The dumbbell of P can have how many orientations? What are the allowed values? It will be plus 1, 0, and minus 1, right? So 3 orientations, namely Px, Py, and Pz. And remember, each one is a space, each one is an orbital. So 2 here, 2 here, and 2 here, totally 6. 2 more here. So far 8. Coming to D. That much was a repetition of the previous page. So now coming to the D subshell. Okay. D, see, can you imagine that the shape is becoming little complicated? From sphere to a dumbbell, which can get oriented in 3 possible directions. It has become complicated, na? So the D is still more complicated. When we move to D, it is still more complicated. Anyway, before going into that, let us look at the possible orientations. What will that be? Plus 2, plus 1, 0, minus 1, minus 2. These are the 5 orientations, orbitals or spaces. Okay. So this orbital can have how many? I will draw the shape later. What is this going to have? This is an orbital, na? ML informs us about orbital space or orientation. So this space will carry how many electrons? 2. So 2 here, 2 here, 2 here, 2, 2 totally 10. So does that not make 18 electrons which were told by Bohr in the third shell? How many electrons? 18. Is it fine? Okay. Okay. Shall we now just shall we go for another 5 or 7 more minutes? Vishak, any problem? You joined little late today. Okay. Now see how we'll use this information so far. We can go on and go for n is equal to 4 also. I have not told you the shapes of D. Okay, we'll do it in the next class because they look little X, Y. If I do it in urgency, you might not understand. Or this is Y, Z, dumbbell, dumbbell. So I'll tell you in the next class. Okay, we'll do it. But currently, and we can go on to do n is equal to 4, or you can do n is equal to 4 and tally that there must be 32 electrons. Please do that. You can also possibly do n is equal to 5 and tally that it is having 50. This will be your homework. So analyze the fourth shell and fifth shell. Let us go to the electronic configuration. Okay. So can we say that the shell number 1 has only S subshell? The shell number 2 has got S and P. The shell number 3 has got S, P and D. Is that okay? Now tell me, in the S subshell of any shell, how many electrons were possible? Should I show you? In S subshell, how many electrons were possible? And in P subshell, how many electrons were possible? Okay, let us go and check once again in the second shell. Check the second shell. In S subshell, how many electrons are possible? And in P subshell, how many are possible? So that's constant, no? So the maximum number of electrons in the S will be always 2. The maximum in P will be 6. The maximum in D will be 10. Okay? Isn't it? In D, check. N is equals third shell has got D subshell having 5 orientations or 5 spaces or 5 orbitals, each orbital having 2 electrons, so a total of 10 electrons. So D in any shell will have 10 electrons. Agree? Okay. Now what we will do? Next thing. Whenever we are giving in the Bohr's model, we used to give the electrons to the various shells. Remember? And we followed one simple thing. Unless the first shell is fully filled, we won't go to the second shell. Remember? Same here also. We will give the electrons to the subshells of the first shell. Once the first shell is fully filled, then we will go to the second shell. And that too in the order of S, P, D, F. S will be given electrons. Then once S is filled, then only P. So let us write the electronic configuration of hydrogen. Hydrogen has got only 1 electron, children. Where will you put them? Can we say it will be put in the shell number 1 and subshell L is equal to 0, namely S. And this whole thing is indicated by the symbol 1s. What is 1? 1 talks about the principal quantum number. What is S? S talks about the subshell. What is this one? This one talks about the number of electrons. So hydrogen's electronic configuration will become 1s1. Clear? So what would be helium's electronic configuration with atomic number 2? The s subshell in the first shell can carry how many electrons? And still one more vacancy is there, no? In hydrogen, is it fully filled? Is S fully filled? So in helium, what will be the configuration? Can we say that both the electrons will be given in shell number 1 in subshell labeled L is equal to 0 or S? So I'll call it as 1s2. Fine. Okay. Lithium, 3 electrons. What will I do? I'll give again same detail. I'll put shell number 1, subshell L is equal to 0, namely S. How many electrons can be there in 1s? 2. I'm still left out with one more electron, no? So where will I go? After filling up the first shell S subshell, I'll go to second shell S subshell. So the configuration further will become 2s1. Yes, Vishak, clear? Yeah, 1s to 2s1. Beryllium, Vishak, atomic number 4. 1s to 2s2. Next one, boron 5. Come on. 1s2, 2s2, because S cannot have more than 2. So you gave 2 to 1s, 2 to 2s. After that, what you will go and use P. What is it called? It's called 2p. It's from the second shell, P subshell. It can have how many? Maximum 6. But how many do I need to fill? Only one, na? Okay. Boron, carbon, 1s2, 2s2, 2p2. Nitrogen, 7. So this will go on up to neon, 10. 1s2, 2s2, 2p6. Fine. The P will start filling up. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Clear? Okay. Then comes sodium with 11 atomic number. What will you do? 11. So 1s2, 2s2, 2p6 allows 10 electrons. So 1s I used, 2s I used, 2p I used. After that, which one will I use? So it will become 3s. Clear? And this can be continued till argon up to atomic number 18. Please do that. Okay. After argon, the rules will not allow us to smoothly fill in the order that is given here. We will have to follow some rules to modify the electronic configuration. So smoothly you can go in for electronic configuration up to argon. Is that clear, children? Okay. So when I look at carbon's electronic configuration, it is 1s2, or I'll put neon's electronic configuration. In neon's configuration with 10 electrons, it is 1s2, 2s2, 2p6. What does it mean? The S subshell has only one orientation. I'll put one box. This is called box diagram. This S also has got only one orbital. Remember, L is equal to 0 represents S subshell. So ML values will be 0 only. One orbital, one orientation, one space. That one space is diagrammatically represented with a box. So if L is equal to 1 represents P subshell, then what are the orientations possible? Isn't it +1, 0, -1? And we know the shapes. Instead of drawing the shape, I'm going to give you the block diagram saying that these are the p subshells. The subshells or the orbitals do not look like these. These are only representations. Clear? Instead of drawing px, py, pz, it will be always tedious for me to do it. Na? So we draw this diagram. So there are two electrons. How do I represent 1 and 2? One with upward half and the other one with the downward half arrow, indicating that it is clockwise. The first one is clockwise spin. The second one is anti-clockwise. Clear? So 2s2, 2p6, 2p6, 6 electrons. 1, 2, 3, 4, 5, and 6. Is it okay? So the moment you see 2p6, you should understand that it is coming from the second shell, p subshell. Therefore, it should have L is equal to 0, sorry, L is equal to 1. So there are three possible ML values, +1, 0, -1, each one containing 2, 2, 2, and therefore 6 electrons. Is the breakdown clear? Okay. So we are stopping with this and we'll continue in the next class. Okay. So today is Tuesday, so we'll again see you on Wednesday. Fine. Okay. Yes. Bye.